Hello everyone. We are going to have another presentation of the Programmers Club where Eduardo Cristo will talk about the fast 2D Gaussian process method based on Celerite and some applications to exoplanet discovery and characterization. So, the stage is all yours.
Thank you, Andre. So hi everyone, today I will present implementation that maybe some of you already know. In our research activities, we often cross with data that presents random white noise and we can deal with it rather easily. The main problem arises when the noise is correlated as it requires us more in-depth analysis of the problem. I'll show how 1D Celerite works, its principles, and how we can generalize it for 2 dimensions. Also, I'll discuss a bit how it can be used in the context of transit photometry and some other interesting applications. So let's start to talk a bit about how the Bayesian framework works. If we have a time-ordered data set with associated uncertainties, describing the relationships between the variables of the underlying model can be a bit challenging. In principle, it is possible to fit a nonlinear functional form, such as a sinusoid or a polynomial function, to describe the variation of the variables with each other. A non-parametric approach can also be followed, adopting a set of nodes across the variable space and use a spline or a kernel to describe nonlinear relationships. One more alternative is the Bayesian strategy, which is able to directly model the underlying function. In this approach, it is necessary to specify a full probability model for the problem and assign probability densities for each model and non-variable. For this, we can employ Gaussian process models, for example. Attributing the probability distributions to the variables as the problem of resulting in an infinite set of solutions that we have to solve in a finite amount of time. Gaussian processes solve this issue, though, despite the variables being described by probability distributions. A stochastic or randomly defined process specifies the properties of them. To depict this, we can think of any given real function as a vector that, with discrete inputs, maps an output vector with the same dimension. Then, if we have a finite number of entries, the data, the inference in the Gaussian process, gives the same answer as we will consider all the points. So, Gaussian processes models contain a mean function with input coordinates x, a covariance and a kernel function parameterized here by theta and alpha. Assuming that we have a data set y under this model, the log likelihood allows one to infer the model variable's value from a set of observations. This is in particular interesting as it can be derived as a generalization of the chi-squared algorithm to include the effects of correlated noise in the data. The residuals vector is computed as the observed data difference to the mean expected model at the corresponding coordinates. In particular, the computation of the distribution requires the inversion of the covariance matrix that is represented in the equations by K. That can be a computationally expensive process for a random n-dimensional problem. So to solve this kind of problem stated earlier, Celerite is an approach that provides a scalable method for Gaussian processes, regression in 1 dimension with implementations in C++, Python, and Julia. In general, the Gaussian processes class of model scales in terms of processing requirements as the cube in terms of memory, and in terms of memory as the square of the number of data points. Celerite presents a method that scales linearly with the data and explores the structure in the problem when the covariance function is expressed as a mixture of complex exponentials without constraints in sampling or noise uniformity. The specific model for the covariance, although associated with some limitations that we'll see next, increases the computational efficiency in many astrophysical problems that are in general time dependent. The one-dimensional nature is the main limitation, constraining the input coordinates to a vector of scalars. This is less of a problem in the cases I stated. So now stay with me a bit along these equations. So the covariance functions that can be expressed, the covariance functions can be expressed as a sum of complex exponentials have been explored by Rybik and Press, which presented a method to scale the matrix inversion computation, scaling the requirements to the number of points instead of the cube. The kernel incorporates the uncertainties at each data coordinate that is represented by sigma. The main idea is to express the kernel as a tridiagonal matrix, which requires a small number of operations to invert. To expand the applicability of the model, it can be generalized by mixtures of exponentials, summing over the first kernel. So we are summing over many kernels of the first type. The generalization can be taken further, expressing each coefficient as complex parameters. So the complex components in the trigonometric form, the autocorrelation structure is defined by mixture of quasi-periodic oscillators, as you can see in the first kernel. The argument inside the sum is denominated as Celerite term in the original Foreman-McKee et al. Paper. So this term in general allows us to simplify a lot the matrices, and the inversion is much simpler and quicker. Written like this, as I stated before, the scaling is proportional to n, as the kernel is positive definite. The power spectrum from the Fourier transform of this covariance function corresponds to the power spectral density. There is no immediate obvious interpretation of this PSD until we set the complex component B to 0 for some component J. The Celerite term is reduced to the product of an exponential, with a sinusoidal function, and the power spectrum takes a form that can be interpreted as the sum of two Cauchy distributions. If we go one step further and set both imaginary components to 0, the power spectral density is compatible with a model that is often called the non-Stein-Uhlenbeck process. Back to the title of this presentation, we'll see that the application of the Celerite method to two input dimensions. To perform this extension to the second dimension will be typically this second dimension will be typically much smaller than the first one, and corresponds to the variability of the correlated noise. Similarly, the kernel function that defines the kernel covariance matrix can be represented as above. This one expresses the covariance between any pair of observations as function of their separation in time and space. A typical scheme to estimate parameters of a model involves the choice of a suitable kernel function to describe the correlated noise, then to define the model that describes the underlying physical process to use as a Gaussian process mean function. After this, we maximize the GP likelihood with respect to the parameters of both the physical process and the kernel function. And finally, and optionally, we can use a Monte Carlo method to sample the posterior and estimate the uncertainties of both physical model and kernel parameters. Now we can discuss a bit how this can be applied to transits before generalizing to 2D. So the search of transits in light curves relies on positive identifications when the depth or duration is large enough when compared with the amplitude and timescales of noise. Here, noise will be taken in a broader sense, as it can be instrumental, and as an example of it, we have photo noise, or that's astrophysical in nature, for example, from atmospheric instabilities in the photospheres of stars. The noise can be also classified as uncorrelated. Again, the photon noise is an example of it, or correlated like the one caused by activity. The main issue we encounter in correlated noise is that it can't be attenuated with larger observed flux by its nature. It can be mitigated otherwise performing multi-waveband observations that disentangle its variability with the wavelengths from the transit. So the first description of how Celerite can be used in this context came in the original paper as the analysis of stellar variability. Following the description of Anderson and Jeffries, stellar oscillations can be modeled in a first approach as the result of stochastic excitations that are damped by convection and turbulent viscosity in the star, which can be modeled by the above differential equation. Here, epsilon of t is a stochastic driving force that can be Gaussian distribution in nature. So as a result, the differential equation solution is a Gaussian process with the power spectral density that depends on a quality factor Q. If we take the quality factor as the inverse square root of 2, the expression simplifies again, and the result is an analog to an Ornstein-Uhlenbeck process that I showed you before. The corresponding kernel taking the inverse Fourier transform is as before expressed as a product of exponentials and sinusoidal functions. So we are going a bit backwards when compared with the first approach that I showed you. To analyze the variability in two bands is equivalent to express the power spectrum density in two components, hot and cold one, that are variable in wavelength. The flux in each band has the contribution from both components at different temperatures. So we are more or less thinking about a photosphere that has an underlying temperature that is in general larger than the top of photosphere temperature. So we have different physical phenomena contributing to the noise. But as both of them are wavelength dependent, the weight is different, and it allows us to disentangle each one. With that X representing in the covariance the spectral coverage of each layer, the corresponding flux varies coherently with this power spectral density. Here we represent the time dependence in X as the cold component, but the relation between the cold and the hot component is only X of C is equal 1 minus X of H. So the sum of the two has to be 1. The amplitude of the variability is set by the contrast between the hot and cold components of the photosphere in each band. As the spectral coverage is time dependent, in particular in this covariance expression, in terms of the cold component, it is drawn from a one-dimensional Gaussian and then described with the Celerite method. Now we'll see how we'll do it. So, as discussed in the one-dimensional case, Celerite takes advantage of representing the GP covariance matrix in a way that the number of operations to invert it is small. In particular, it will result of the sum of a diagonal matrix and J semi-separable matrices. The semi-separable matrices can be factorized using the Cholesky method, and the computation time will be of the order of number of semi-separable matrices times the number of observations. So it is proportional, as stated before, to n. It can be then rewritten in terms of two generator matrices, U and V, along with the diagonal matrix that is here represented by A. The trill and true operators replace with zeros the portion of the matrix above and below the diagonal. The main thing to retain here from this expression is that the generator matrices are sums of products of exponential, by sinusoidal functions, and then can be expressed with Celerite formalism. Loper et al. Proved that Celerite kernels provide a complete basis for one-dimensional stationary covariance functions. Then these methods can in principle be used to approximate any stationary kernel. Now we are then ready to decompose the 2D problem in terms of the 1D formalism. Similar to the matricial decomposition that was performed before, the 2D problem kernel can be written in terms of diagonal upper and lower triangular matrices using the trill and true operators. The second dimension covariance term is accounted by the diagonal matrix R, represented there in the 2D kernel, and its decomposition in terms of the vector alpha product with this transpose version, so alpha and alpha transpose. Using the formula for mixed Kronecker and matrix products, the kernel takes the above form that simplifies in a rather elegant way. The Kronecker products can be expressed in terms of A comma, U comma, and V comma with the same structure of the 1D problem. The computational cost grows the same way as before. The only difference now is that we have to perform additional Kronecker products in these matrices that are not very computationally expensive. The new generator matrices updated by the second dimension have the same structure as the one-dimensional counterparts. For these two-dimensional Gaussian processes, the set of observations to compute the GP likelihood is also two-dimensional. This requires it to be reduced to one dimension. So now let's evaluate how good is this approach with the ratio between the correlated and uncorrelated noise in this specific problem. So to summarize, we have a stellar atmospheric model with two temperatures. We have two types of noise, one correlated and the other one is uncorrelated, and we are trying to disentangle them. So if the uncorrelated white noise dominates, the measurement of the transit depth and time parameters is similar in the two-band case and the monochromatic case. So it's the first row. As the correlated noise starts to dominate, the monochromatic case is a worse approach, and the two-band model improves the measurements in some cases by 1 or 2 orders of magnitude. This is very important if we have a low signal-to-noise ratio, for example. When comparing the Monte Carlo Markov chain uncertainties represented by dots here, and the information matrix uncertainties that are represented by lines, there are clear differences. For these simulations, the correlated noise is 155 and 50 times larger than the uncorrelated noise. The uncertainties don't match globally well up to log transit signal to noise ratio of 0.5 in contrast with the two-band model at much lower signal to noise ratio. This is somewhat an evidence that the two-band approach is superior in correlated noise dominated cases where signal to noise ratio is critical. Some exciting applications are areas that depend highly on the signal to noise ratio. So areas where we have just enough to try to characterize some physical phenomena. Exomoons are theorized to exist, but are up to date unconfirmed. One of the main limitations is their size and corresponding shallow transits. Furthermore, we can't phase fold the transits like we do for the planets, because these bodies are orbiting a second one, the main planet. So we don't have any method to increase the signal-to-noise ratio over many transits. Exorings have similar problems with increased complexity on the transit model. So we are increasing in principle, and if we have low signal-to-noise ratio data, the uncertainties overall. Regarding transmission spectroscopy, or the measurement of the apparent radius of planet in multiple bands, the variations detected are small and often accompanied with larger error bars. It is yet, at least in my view, to define how this model can be used, as both variability and radius present a wavelength dependence. If the data is not good enough, increasing the number of parameters can create degeneracies that when compared with one layer model. Furthermore, we have many more applications. Of course, I talked about here the most exciting ones that are that have the highest impacts, but I can imagine you can find many applications for Celerite, as most of us have Gaussian, we use Gaussian processes um, when working in the most plural problems in our research. So thank you. I would appreciate you to have some questions.
Thank you, Eduardo, for your nice talk. If anyone wants to ask a question, please feel free to do so.
Hi, Eduardo. Thank you for the very good presentation.
Hi, Akin. Thank you.
So I just had some questions about this your last slide. So a common,
Oh, this one?
yes, yes.
Okay.
A common fear that people have when it comes to GPS is the fact that there's a possibility that you can potentially remove every interesting thing from the light curve, like moons and rings, and you'll be left with just the basic light curve of a planet. How does one mitigate against this kind of things?
The problem, you have that kind of problem, I think, when the problem you are analyzing is not stationary in time, right? That is a problem for moons, for example. I know that you work with rings. I'm not sure how is the geometry of the problem, but I can imagine that if you have a transiting planet with a ring, it will always present the same tilt in several transits, or not?
Yeah, pretty much.
Okay, so you can use, for example, phase folding for in that particular case, right?
Yes, but these signals are really small,
Yes.
and there's a possibility that it's somewhat just a little bigger than the variability of the star itself. So if you're fitting a GP to it without simultaneously taking into account the rings to try to fit them together, then you can remove the ring signal with the GPs.
Yeah, of course, if the amplitude is similar to the activity, this method is not good for you. So you have to have some separation between them. But I think you can study that if I think you are able to study that at least numerically, right? You can assume some type of ratio between correlated and uncorrelated noise, and see if the planet signal is in amplitude larger than the noise, right?
Yes, that is true. One other thing that people do, I don't know if it's completely commonplace, is to assume some parameters for the transit model already. So to fix some of the parameters like the period, the radius, the depth, some of these parameters, all the rings in this case, then try to model the variability with GP, right? After which, when you then have some parameters of the GP, you can perform a simultaneous fit using the constraints from the previous fit. In that way, you kind of you kind of make sure that your GP is not trying to interpret everything it is.
Yeah, that is true, but can also be a problem. If we see the comparison, for example, this one, the impact of the two model photosphere is different for different parameters, right? So if you are computing, for example, the mid-transit time with a monochromatic approach, you can be making a wrong estimate when compared with the two model of the photosphere. So I don't think it's a good approach in this case, but we can discuss it, to fix these parameters in particular. The radius has the impact on the radius is not very large, as you can see. It's less than 10% in this case. But in T0, I think it's quite a lot.
Yeah, that's true.
But I don't think it's a good approach, or at least we could study if this model changes by a large amount the estimates that we have from the monochromatic model. If they are very different, something is happening, right?
Yeah.
Because both converge when the white noise dominates. So we can have something, some underlying process giving, making that difference larger.
Okay, thank you.
Thank you, Hakim.
Eduardo, let me ask myself a question, or ask you a question. So, do you have an idea of how large the impact is when approximating a stationary kernel with Celerite comparing against using the actual kernel itself? Do you have any way to measure that difference or to estimate what it would be?
In terms of output of results, right?
Yes.
No, I'm not sure if that is discussed in the paper. I focus more on the difference in the parameters than in the difference between a stationary kernel when compared with this one. But maybe, well, when do you use a non-stationary kernel?
I was not talking about non-stationary kernels. I was talking about, so Celerite approximates a stationary kernel using the methodology that you described.
Yes.
So what is the difference of using this approximation against using the real kernel that we're approximating?
Okay, only approximation compared with the
Yes.
with the stationary one.
Yes.
Well, they discuss it a bit. If I am correct, they say that there is some difference if the number of inputs is low. So if your data set is not large enough, this approximation is not good. Also, yes.
Sorry, I was just commenting that in that case it wouldn't be worth it to use an approximation if you have a low number of input points.
Yes.
Your kernel will be fast. You'll not have a problem with inverting the
So
matrices.
it's not really a problem, right?
Yes. In that case, no.
I'm not sure if they discuss, I don't remember if they discuss more than that, but at least they state that.
Okay, thank you.
But it is very good, right?
Yeah.
If this is as they show, right? We have a lot of benefits doing the Celerite method. And the Celerite method is very general. They apply this for the transit light curves, but it can be used in astrophysics or any other physics area, I think. When you use Gaussian processes, I think if they are stationary, I think you can implement it.
Yeah, it makes sense. Okay, thank you.
Thank you.
So does anyone else have a question for Eduardo? Well, it appears that there are no more questions, so we will finish here this presentation. Once again, thank you, Eduardo, for the nice presentation, and we will see you sometime in the next. Thank you all. Stay safe.